This is section 10.3, and this is on applications of quadratics. So this whole section is going to be a bunch of word problems that once you set up the equation, that equation is going to be a quadratic. So let's just dive right in. The length of a rectangular field is 6 meters longer than its width. If the diagonal footpath from one corner to the opposite corner is 30 meters, what are the dimensions? So when it asks for the dimensions, it's asking for the length and the width. Let's draw a picture of what we got first. So we know it's a rectangle, and we know that the length is 6 meters longer than the width. So here's what we got. We know that that diagonal footpath from one corner to the other is 30. Now how did I know it was this diagonal and not this one? It doesn't matter. You can use either one. So in doing this, because it's a rectangle, we know these are right angles in the corner. So this forms a right triangle. A right triangle, we know we can use the Pythagorean Theorem on a right triangle. The Pythagorean Theorem says that the sum of the lengths of the squares of the two legs is equal to the square of the hypotenuse. Okay? So I've got this width and this length. Now notice I didn't use another variable here. I do try to keep it to one variable. So I didn't use an L here. I used the fact that the length is 6 meters longer than the width. That means that the length is W plus 6. So I end up with this right triangle. This is going to give me my quadratic here by substituting this into the Pythagorean Theorem. So remember, leg, the legs make up the right angle. The hypotenuse is this diagonal component right there. So substituting W in for one leg, W plus 6 in for the other, and 30 for the hypotenuse, we get this quadratic. So now the new part of this section is now done. The new part was taking a word problem and translating it into a quadratic. At this point, it's solving a quadratic. So here's what we need to do. We need to multiply this out, and then we need to combine like terms to get this into standard form, which is ax squared plus bx plus c equals 0. Now, be careful. When you go to distribute this out, this is not w squared plus 6 squared. You cannot just distribute that squared. Instead, you have to multiply it by itself, right? Squared means that thing times itself, and then FOIL, or distributive property. In doing so, we get that this part right here expands into that, and then distributes out into those four terms. We can then combine like terms. We have two w squared terms and we have two w terms here. So we can combine those like terms. Now I can move this 900 to the other side, and that'll get my quadratic equation equal to 0, that standard form that we need. Remember, once we get it in that equal to 0 form, then we can factor it or use the quadratic formula. So I move that 900 over and then combine those like terms. So 36 minus 900 is that minus 864. Now at this point, you could go straight to the quadratic formula here. So if you just really wanted to, you could go straight to the quadratic formula right here. A is 2, B is 12, C is negative 864. I chose to factor it, but you certainly don't have to do it that way. So I took out the 2 first, that GCF, then divided both sides by 2. Because it's an equation, I can do that. And this 0 divided by 2 just gives me 0. Now, at this point even, you can factor it, you can complete the square, or you can use the quadratic formula here. You could have also used the quadratic formula up there. It would have been messier because you have bigger numbers. By taking out that GCF, you know, I got it down to a nicer quadratic that has the same solutions. So I chose to factor it. this is trial and error, so I had to find two numbers that multiplied to give me negative 432 but added to give me 6. And those two numbers were 24 and negative 18. Then splitting those apart, I got W equals negative 24 and W equals 18. Now here's the thing. We know that the width is not going to be negative. We're talking about, a rectangular field. So it's not going to be negative, so it must be the 18. Then coming back, there's one dimension. What's the other one? Well, there's the width. So what's the length? Well, remember, the length was 6 meters longer than the width. So adding 6 to this answer, we get a length of 24. It does happen quite frequently that this negative answer that you cross off tends to be, this other answer, but it's not enough times that I would guarantee it. But if you notice it happening a lot, just kind of be like, oh, that's interesting. But it's not enough that I would say, hey, you know what, you can just make that positive and that's your other answer. Not enough. I don't feel good enough about saying that that's always going to work. All right, let's do another example here. This one's a little less menacing. A positive integer is one more than twice another. Their product is 78. Find the two integers. All right, we got to set up an equation here. So, a positive integer is one more than twice another. Remember, twice means 2 times. So I'm showing you how this English translates into this math. Okay. Now at this point, I am using 2 variables. I'm using x and y. I'm going to compress it into one variable though. Their product, that means multiply, is 78. So the first sentence was this equation. My second sentence is this equation. Now, do you guys remember how we solve a system of 2 equations and 2 variables? We use substitution. So I am going to eventually get rid of one of those variables. If you wanted to do something with substitution in example 1, you could have. I chose not to. I chose to just set it up in a different way. But if you choose to do it, by using substitution in example 1, that works too. So there's my 2 equations, and you guys remember back in chapter 8, we use substitution. So look, this one's already solved for x, so I'm going to substitute that into there, sticking with my same color scheme as before. I substitute that in for x, and then I'm going to distribute out that y. I'm going to move that 78 over. Now it's in standard form. At this point, you can factor it, complete the square, or use the quadratic formula, whichever one you're most comfortable with. All right, so with this one, I factored the last one, so let's use a quadratic formula for this one. So here's my quadratic formula. Now, I initially accidentally wrote x equals when I was writing that quadratic formula, and I had to go back and change it to y. Do you know why? Well, because the equation that we're solving, let's go back and look. Look, see the equation that we're solving? It's a function of y. So that means that the quadratic formulas give me solutions for y in this case. So I just wanted to point that out because I put x there not even thinking, and you can see I put x all the way down there and was like, oh no, wait a minute, that's not right. All right, so going back to that previous equation, we had an a value of 2, b was 1, c was negative 78. So again, that comes from this equation down here. Doing some plug and chug here. You can use the calculator to simplify this discriminant. Remember, the discriminant is just the stuff under the radical. So I use the calculator to do the 1 squared minus 4 times 2 times negative 78 to get 625. The square root of 625 is just 25. So this right here splits into 2 solutions. Right? Remember, it splits into the positive and the negative. So the negative 1 plus 25 over 4 and the negative 1 minus 25 over 4. That gives me 24 over 4, which is just 6. This gives me negative 26 over 4, which is a negative 13 over 2. I'm going to cross this one off. Not because it has to do with any kind of length, or anything like that, but because the original problem said positive integers. So that's why I'm choosing that positive answer. So I get that from the quadratic formula that y equals 6. Now, going back to my substitution, remember that thing that I substituted, and plugging that y in, now I can get the x value that corresponds with this y equals 6 business. So there's the two positive numbers. Okay. The sum of a positive number and 14 is 735 times the reciprocal. Find the number. All right, so here's the equation that results from this. The sum, that means add, of a positive number and 14 is 735 times the reciprocal. The reciprocal is 1 over a number. So remember, the word sum means add. The word is right there is why I put the equals. I put that because it says times, and then that was the reciprocal. Now, if you multiply 735 times 1 over x, if I put that over 1 and I just multiply fractions by straight across the top and straight across the bottom, I'm going to get this more simplified fraction. So I get x plus 14 equals 735 over x. Now, if I multiply both sides of that equation by x, because you may be thinking, wait a minute, I thought this had to do with quadratics. I don't see a quadratic anywhere because there's not an x squared. Well, it's coming. I'm going to multiply both sides by x. So this x right here is this blue, is why I'm multiplying by that blue x. So those x's will cancel. And then distributing that out, now I got something that looks more like a quadratic. I'm going to move that 735 over, and that'll get me in standard form. I'll get that quadratic equal to 0. All right, at this point, you can factor it, complete the square, or use the quadratic formula, whatever you're comfortable with. I chose to factor this one. I'm kind of going back and forth between factoring and quadratic formula, just in case some people are more comfortable with factoring. Maybe some people are more comfortable with quadratic formula. If you like completing the square, well, you just go be weird, because you're like the only one out there that wants to do it. But hey, you go be you. So looking for two numbers that multiply to give me negative 735 and add up to give me 14. It's these numbers. And really, I just used the calculator to guess and check that. So you may be like, why in the heck did she do factoring, and how did she know these? I just used, I saw this was a 5, so I just started like dividing it by 15, 25, 35, just trying some stuff out. Okay, so once you get it factored, you split that apart, you get negative 35, and then you get positive 21. I'm going to cross that one off because the original problem said positive. So it said the sum of a positive number and 14 is 735 times the reciprocal. Okay? So find the number. There was just one answer here, not two. So there's nothing to have to plug back into. Okay. Example 4 is going to utilize the Pythagorean Theorem again. A right triangle has two equal sides. The hypotenuse is 14 centimeters. Find the length of the sides. All right. So here's what the Pythagorean theorem is going to look like. How did I know that it was these two sides that were equal? Well, because in a right triangle, the hypotenuse is always the longest side. It cannot possibly be equal to any of these. So it has to be those two legs that are equal. If two sides are equal in a right triangle, it has to be the legs. So the Pythagorean theorem says that leg squared plus leg squared is hypotenuse squared. All right, and I just called that missing length there x, and I called it, x and the same x for both of these because it says two equal sides. Adding those two up, I get 2x squared equals 196. Now check it out. I'm not going to move that 196 over and get that equal to 0. Why? Because I can use the square root property. If I divide both sides by 2, I get x squared equals 98. If I don't have an x term, I can use the square root property. So that means I can just take the plus or minus square root of both sides. All right, so I get plus or minus the square root of 98. That does simplify. So if you do the square root of 98, you're going to get 7 root 2. And I went ahead and just showed you the behind the scenes action of how you get 7 root 2. Remember, it is a plus or minus. When you do the square root property, you need that plus or minus. So I have two answers, the plus and the minus. Which one is it? Well, we're talking about the length of the side of a triangle. It has to be positive. So it's going to be that 7 root 2. Remember, you can always pause if you feel like I'm moving kind of fast here. You can always pause it and hit rewind. Example 5. It costs Mrs. Smith $3 to build a picture frame. She estimates that if she charges X dollars for each one, she can sell 60 minus X frames per week. First of all, does anybody really do this? I mean, like, is this even, like, who's like, if I charge X, I can sell... Right? I prefer much more realistic problems than this, but here we are. So I know this kind of stuff is going to show up in Hawk. So I just want to show you how to set this one up. What's the lowest price necessary to make a profit of $432 each week? Okay. So just so we're clear here, I'm just labeling all kinds of stuff. X is the price for each frame that each frame sells for. Okay? And I know that ending with a preposition is terrible, so just forgive me for that. It's $3 to make each frame. So her profit for each frame is X minus 3. Now, how did I get that? Well, if she sells it for, let's say, $10 and it cost her $3, then she profits 7. So whatever she makes on it, right? However she sells it for, minus her cost is her profit. So this stuff you had to figure this out. This is how many frames she wants to sell. So your total profit you want to be $432. So how do you calculate your total profit? Well, you figure out how much you profit on each frame times the number sold. This one's a hot mess, okay? Let's not even lie to each other. Let's not kid each other here. This one's a mess to set up. Once you get it set up, it's not as bad, right? Because it's just, your standard operating, quadratic. But getting this set up is a bunch of hot garbage here. So, all right, so again, total profit is the profit you make on each frame times the number of frames that you sell. We know how many she wants to sell from the problem. The profit, we had to figure that out based on the price that it sells for and the cost to make it. So profit is always the sale price minus the cost. Okay, so now we're just going to distribute this out, combine our like terms, get it in that standard form. So distributing this out, we get this left-hand side. We got some like terms. And I went ahead and put them in descending order, with the squared first and then the x. And I moved that 432 over. So a lot happened from here to here. So if you have to pause right here and say, whoa, what happened? A lot happened. I combined the like terms to get 63x. I moved that x squared to be first. And I moved that 432 over. And then I'm going to combine those like terms, those constant like terms. So I get this. Now, I really don't like having a negative out in front of the x squared. You can use the quadratic formula with a negative right here, okay? But you have to be really, really careful when you're doing that. So I chose to divide each term by -1. You didn't have to do that. You can use the quadratic formula right here as it is. Okay, so you can use the quadratic formula here without dividing. by negative 1. You can go ahead. A is negative 1, B is 63, C is negative 612. I chose to divide it by negative 1 and then use the quadratic formula. That's because it's going to be messier. With that A being a negative, when you start going through the quadratic formula, having a negative in the denominator messes a lot of people up. So while it may seem confusing, like why did she divide by that negative, I feel like that step is less likely to cause you problems than leaving the negative and having to contend with it later. All right, so using the quadratic formula and using the calculator right here to simplify that discriminant, I get 1521. The square root of 1521 is 39. This splits up into two answers, 51 and 12. Now, how do I know which one it is? We've been crossing off the negative or, whatever. Well, how do I know? Both of these are positive. I chose 12 because the problem asked for the lowest price. So both of these prices will provide, the stuff that she was looking for. But the 12, that's the lowest price for which all those conditions will be met. All right, so that concludes section 10.3.